This is a very beautiful problem from RMO 1994, the Regional Mathematics Olympiad of India. Problem number 6. It can be done simply by using angle chasing and a property that is sometimes missed out by beginner problem solvers, which I call perpendicularity. It's a very simple idea. It's sort of a heuristic observation. I'll tell you what that means, okay? So let me first give you the given data of the problem. So we have a circle and we have two chords AC and BD, which are perpendicular to each other. O is the center of this circle and AB, CD, we join them. Suppose K is the midpoint of AB and L is the midpoint of CD. Then we want to show that 𝑂𝐾𝐿M is a parallelogram. So first thing we know that AC is perpendicular to BD. The second thing is KL are midpoints. And the third thing is O is the center. Our goal is to show 𝑂𝐾𝐿M is parallelogram. Okay, so how do we do that? Well, there is a few things that you have to notice, that Km is equal to Kb is equals to Ka. This is a standard property of right angle triangles. But if you have a right angle triangle, let's say XYZ, and if you take the center of its hypotenuse, let's say R, then R is the circumcenter of XYZ, which means that R is equidistant from the three vertices, which means that Rx is equals to Ry is equals to Rz. So I can easily say that these two red angles, these two red angles are equal, and I can easily say that these two blue angles are equal. Okay, because Ka will be equal to Km, so this is an isosceles triangle. K is the circumcenter, it's the midpoint of the hypotenuse. So K is equals to Km, so these two angles are equal. Kb is equals to Km, so these two angles are equal. Okay, now one more thing is that BC, this arc, subtends this blue angle on the circumference. So it will be also equal to this angle here, the other angle that it subtends. So other blue angle. Okay. Moreover, notice that L is the circumcenter of MDC. L is the circumcenter of MDC because it's again the midpoint of the hypotenuse of this triangle. So these two angles are also equal. The LM and LD are equal because they are the radius of this right angle triangle, So LM is equals to LD means these two angles will be equal. So all of these blue angles are equal. That's what I mean. Similarly, one can show that this red arc subtends this red angle here. It also subtends the same red angle here. So this angle is also red, and again LM is equals to LC, so this angle is also red. Okay, so we have all the angles color coded, the angles that we want. Now what I will do is I will use the green color to extend LM and meet the line AB at some point R, capital R. Okay, so one thing you notice that RL and BD are intersecting each other, right? Which basically means that this angle is also the blue angle because they are vertically opposite. Okay, so now focus on this triangle RBM, the triangle RBM. We have one blue angle, one red angle. So what should be the remaining angle? This remaining green angle, what it should be? It must be 90 degree. Why? Because notice in this big triangle, one angle was red, one angle was blue, and the remaining angle is of course 90 degree because we already know that AC and BD were perpendicular. So the blue and the red must be together equal to 90 degree. So now focusing on this smaller triangle, here also the red and the blue must be together equal to 90 degree, making the green as 90 degree. Okay, so this means that LR, or you can say LM, is perpendicular to AB. Now this is something I mentioned in the starred notation. Sometimes we miss this idea that two lines which are not intersecting, we can think about their directions of motion and still say that they are perpendicular to each other. That is LM and AB in this case. AB was like this, LM was like this. One of the things that we can always say in which direction you are moving if you go from L to M. And that direction could be perpendicular to the direction of motion of AB. So you have to have a dynamic picture in your mind. One way to see this perpendicularity is of course extend LM and make it actually hit AB, which we did in this problem, and show that it is indeed perpendicular. Now OK is perpendicular to AB. OK is perpendicular to AB because O is the center, K is the midpoint of a chord. So it's a standard theorem that center to the midpoint of the chord, that segment is always perpendicular to AB, the chord itself. So OK is perpendicular to AB, LM is perpendicular to AB, that we just proved. So these two sides must be exactly parallel to each other. Now I showed that LM is parallel to OK. You can exactly the same way you can show that KM is parallel to OL. You have to again extend KM to hit this line DC. So can you put an argument in the comment? Why would KM be perpendicular to CD? It's exactly the same way we did the OK perpendicular, LM perpendicular to AB thing. Now if you can show that OK is parallel to LM and KM is parallel to OL, because KM and OL are both perpendicular to the same line, so KM is parallel to OL, then if both pairs of sides are parallel to each other, then that's a parallelogram and we would be done.